Hello everyone, welcome to Group 3's presentation on exploring bias in healthcare, where we analyze the diabetes dataset. Let's review the agenda for today. My name is Sanil Edwin and I will take you through the introduction. The dataset exploration portion would be covered by Sergio and Jessica. Bias identification and analysis will be done by Jerry and Selin. Bias mitigation strategies would be covered by Rochelle, and I'll come back for the conclusion. Let's look at an overview of the problem, how we tackled it, and our proposed solutions. This assignment aims to analyze the healthcare dataset related to diabetes diagnosis, exploring the dataset's structure, identifying data quality issues, and assessing potential biases that could impact predictive modeling and healthcare outcomes. Given the increasing use of machine learning in healthcare for diagnostic purposes, it is crucial that we understand the limitations and biases inherent in the data before applying complex algorithms. Misrepresenting or overlooking data quality issues can lead to flawed models that reinforce health disparities or produce inaccurate risk assessments. By examining this dataset, we aim to gain insights into key health indicators associated with diabetes while identifying and addressing unrealistic values, missing data, and skewed distributions. Additionally, we seek to understand potential biases such as selection, measurement, and algorithmic biases that may comprise the dataset's representativeness and fairness of any predictive models built from it. Through this analysis, we aim to develop a more ethical, reliable, and inclusive data-driven healthcare solutions, ultimately improving patient care and health equity.
We first analyze the structure of the dataset diabetes.csv. This dataset contained 768 rows and 9 columns. The columns included features such as pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, age, and outcome. The first 8 columns were numeric, and the 9th column was a binary feature with zeros and ones. We analyzed the distributions of all the numeric features using box plots, as shown on this slide. We identified some outliers, which are the dots outside the whiskers, as well as some impossible values, meaning some features had observations with zero values, which are biologically impossible. For instance, blood pressure, skin thickness, and BMI cannot have values equal to 0. We analyzed the distributions of all the features using histograms. For age and pregnancies, the distributions were right-skewed, indicating that most participants were younger and had fewer pregnancies. For BMI and skin thickness, we found a roughly normal distribution, with peak around 30 and 20 to 30 respectively. For blood pressure and glucose, we also found a near normal distribution, with peak around 8 and the range between 100 and 120 respectively. For diabetes pedigree function and insulin, the distributions were heavily right skewed, meaning most individuals have low values, but some have significantly higher ones. And for the feature outcome, that only had values zeros and ones, most individuals have values equal to 0, and just a small group had values equal to 1.
We analyzed a distribution of the outcome class and found that class 0 has more cases at around 65%, compared to the almost 35% in Class 1. This imbalance could potentially lead to biased models. Now, a correlation analysis showed that some of the features had a high correlation with the outcome variable. Examples of this are glucose, which presented evidence that higher glucose levels are strongly connected with diabetes. There's also a moderate correlation in BMI, showing that a higher BMI is possibly linked to diabetes. We found other correlations that include a connection between age and pregnancy. This presented evidence that older individuals tend to have more pregnancies compared to younger individuals. There's also a correlation between skin thickness and insulin. Higher skin thickness correlates with insulin levels. Impossible values. We assumed 0 values are impossible except for instances of pregnancy, which we will assume negative values are impossible. So we made some observations. There were 5 observations with glucose level 0, but blood glucose is essential for survival. So any glucose value of 0 likely represents an error or missing data. We also found 35 observations of blood pressure equal to 0, but the blood pressure should not be 0 in a living person. 227 observations with a value of 0 millimeters for skin thickness were made, and that is not biologically possible. There were also 374 cases with 0 insulin value. However, this may be valid in certain medical conditions, an example being diabetes type 1. However, in most cases, it will indicate missing data or an error. There were also 11 cases observed with a BMI value equal to 0, but a BMI of 0 is not realistic.
Algorithmic, data-driven, or social biases can impact the outcome of scientific studies. Scientists and data scientists are responsible for designing models or coming up with ways for data collection that minimize bias as much as possible. Here's an example as to why limiting bias is important. Convolutional neural networks were trained to recognize melanoma lesions, but when they were training the model, a very small portion of samples were from darker-skinned patients, so the model could not recognize melanoma lesions in Black people as effectively. And this example shows that racial bias in datasets could easily inhibit people from accessing the medical care that they need. In addition to racial bias, gender bias in data has also caused significant harm in the past. Women showed very different symptoms in the event of cardiac arrest, and when they developed machine learning models to predict cardiovascular events, women were underrepresented in the training dataset, so the model wasn't able to predict these cardiovascular events as reliably in women. Lastly, age is another bias that needs to be considered. Automated sleep scoring algorithms were doing really well on test subjects, but they were failing with real-life patients. And this is because the training dataset only had young and healthy men, even though they were trying to diagnose older men. So it is always crucial to limit these kinds of biases to make sure that medical care is reliable and accessible to all.
My name is Jerry Kim, and I'll be presenting bias identification and analysis as a third step of exploring bias in healthcare, analyzing the diabetes dataset. After my group collaborated in the previous step 2 and performed exploratory data analysis on this diabetes dataset, we realized that there could be some potential biases to be identified. Here are some basic descriptive statistics of the dataset, which actually tell us quite a bit about these potential biases. The first one to address is selection bias, because we believe that the dataset does not accurately represent the population or phenomenon we're interested in, which is presence of diabetes in this case. The very first feature we see here is pregnancies, which can only happen to females, and the minimum value for age is 21, which excludes younger people. The second bias we'd like to address is measurement bias, because glucose, blood pressure, skin thickness, insulin, and BMI all have 0 as their minimum value when it's humanly impossible. When we closely take a look at skin thickness and insulin, their first quartile is also 0, which may indicate missing values rather than actual measurements. The last bias to address is algorithmic bias, because the target variable outcome is binary, either 0 or 1, and yet the mean is around 0.35, which means the ratio of one class to the other class is almost 2 to 1. Such a significant imbalance can affect the predictions of an algorithm to systematically favor a certain group over the other. Next, we visualize and discuss the biases. Here's a heat map for all the zeros, or I should say missing values, in the dataset. Even without knowing the exact numbers of NAs, This heat map clearly shows that skin thickness and insulin especially are just filled with zeros. In case you're wondering, they respectively have 227 and 374 zeros out of only 768 cases in total. These missing values, disguised as zeros, must be handled as a part of pre-processing. Here we have 9 histograms for each feature in the outcome variable so that we can check for skewness in any of these distributions. Visibly, the features like pregnancies, insulin, diabetes pedigree function, and age are highly skewed to the right since their tails are stretching on the right side of the distribution. The problem with this high skewness is that a trained model can make inaccurate predictions for underrepresented values. What adds to such skewness for further bias are significant outliers. This time, we have box plots that are quite useful in detecting which features have extremely outstanding values. Insulin is just going off the chart here, not just the value, but also the number of outliers beyond its third quartile. Other features like blood pressure, skin thickness, BMI, and age all have some outliers that are responsible for the right skewed tails. Such skewed features must be normalized for better modeling through transformation, and a common one would be log transformation. Simple class distribution is for visually checking whether there's really an imbalance between the two outcome classes. Now we can see that the dataset has almost twice as many non-diabetic cases as diabetic cases. Any model trained on this data may output biased predictions in favor of the majority class, which means predicting non-diabetic when a patient actually has diabetes. Additionally, we have a correlation heat map of all 8 features and the outcome variable. This is just an extra step to ensure that there's no multicollinearity between any 2 features. The heat map highlights which features are strongly correlated with one another, as well as with the outcome variable. Depending on the domain knowledge, a moderate correlation between 2 features can signify multicollinearity. For example, BMI and skin thickness have a moderate to strong correlation of 0.65. As a general rule of thumb, the feature with a higher correlation with the outcome would be retained. In this case, skin thickness would be removed for it has a lower correlation of 0.26 with the outcome versus BMI correlation of 0.31 with the outcome. The same idea goes to these bottom 2 correlation comparisons. In a regression analysis, it's important to consider multicollinearity because it undermines the stability of coefficient estimates and makes it difficult to determine the individual effect of each feature on the outcome. Finally, we interpret the biases as the following. Misrepresented demographics, such as gender and age, can lead to selection bias. The dataset only consists of women aged 21 and older, and does not represent other populations including men and younger women. As discussed before, missing values that are disguised as zeros, plus skewness and outliers can all lead to measurement bias. Such errors in the data collection process not only distorts reality, but also affects model performance. Class imbalance in the outcome variable can lead to algorithmic bias, as the model learns from its uneven data. Increasing the representation of minority class through sampling techniques would be essential in improving the balance. Lastly, checking for multicollinearity is needed when there are many features for data modeling. Insulin and skin thickness in the previous slides are selected for removal and also have too many missing values, so we expect removing these 2 features would greatly reduce measurement bias and improve model performance. On this note, let's move on to bias mitigation strategies.
Bias mitigation strategies for the diabetes dataset. Bias in healthcare datasets can lead to unfair and inaccurate predictions, affecting patient care. To improve fairness and accuracy, we must address biases related to missing values, gender imbalance, class distribution, and demographic representation. Handling missing values. The dataset contains unrealistic zero values in critical attributes like BMI, blood pressure, and insulin levels, likely indicating missing data rather than actual medical readings. Why is this a problem? Missing values distort analysis, leading to misleading patterns that can compromise predictive accuracy. How do we fix it? Use median or k-nearest neighbors, KNN, imputation to replace missing values with more realistic estimates. Advanced imputation techniques prevent artificial patterns and improve data reliability. Addressing gender bias. The pregnancies variable suggests the dataset is heavily skewed toward female patients, limiting its generalizability. Why is this a problem? A model trained primarily on female data may fail to assess diabetes risk in men, reducing its overall effectiveness. How do we fix it? Supplement with male patient data from external sources. Use data augmentation to synthetically generate male patient records and improve gender representation. Balancing outcome classes. The dataset contains 500 non-diabetic cases versus 268 diabetic cases, creating a class imbalance that can skew predictions. Why is this a problem? The model may favor the majority class, leading to false negatives where diabetic individuals go undetected. How do we fix it? Apply synthetic minority oversampling technique, SMOTE, to generate additional diabetic cases. Use cost-sensitive learning, penalizing misclassification of diabetic cases to improve detection rates. Ensuring fairness across demographics. The diabetes pedigree function variable reflects genetic risk, but if certain racial or ethnic groups are underrepresented, the model may learn biased patterns. Why is this a problem? Underrepresentation leads to systematic misclassification, where some groups receive less accurate predictions. How do we fix it? Implement fairness-aware algorithms, such as adversarial debiasing, to adjust predictions equitably. Collect more representative data to improve model fairness across populations. Ethical considerations. Bias mitigation is both a technical and ethical responsibility. Key principles include utilitarianism, maximizing overall predictive accuracy for the largest number of patients. Kantian ethics, treating fairness as a moral obligation, ensuring equal consideration for all. Virtue ethics, promoting transparency and inclusivity in AI development. Conclusion. By addressing missing data, gender bias, class imbalances, and demographic fairness, we improve model accuracy and equity in healthcare predictions. However, bias mitigation is an ongoing process. Continuous monitoring, ethical AI development, and inclusive data practices are essential to ensuring fairness in healthcare decision-making.
In conclusion, our exploratory analysis of the diabetes dataset has revealed critical insights into the data structure, biases, and potential implications for predictive modeling in healthcare. The examination of key features highlighted the presence of biologically implausible values, significant outliers, and class imbalances that pose challenges for accurate diabetes risk assessment. The proposed bias mitigation strategies, including handling missing values, addressing gender imbalances, balancing outcome classes, and ensuring demographic fairness, are crucial steps towards enhancing the dataset's integrity. As we move forward, it is essential to prioritize the implementation of these strategies, fostering collaboration among data scientists, healthcare professionals, and policymakers. By addressing the biases inherent in the dataset, we can improve the accuracy and reliability of diabetes predictions, ultimately leading to better health outcomes for all individuals, regardless of their demographic background. The journey towards unbiased, data-driven healthcare is ongoing, and our commitment to ethical practices will be vital in shaping a more equitable future in medical predictions and interventions. Thank you.